We'll start in 1 minute. Today we'll cover section 3.6. This is the last section that we'll cover this semester. It's on modeling with exponential and logarithmic functions. Remember, quiz 10 today at about 11:40. 1 week from today will be test 3. That will be over the chapter 3 material. There are currently 2 playlists on YouTube that cover the test 3 material. Math 1143, Chapter 3 material, Test 3 material, and then the Math 1143 Test 3 review sheet videos. If you want to get a head start, you can look at those. And next Monday and Wednesday, we will review for Test 3. But today we'll cover section 3.6. In Objective 1, we solve what are called literal equations for specified variables. In this first equation, from the field of medicine, solve the equation capital L equals 10 times the base 10 logarithm of capital I divided by capital I sub 0. Solve that for capital I. Okay, so we want to solve for capital I, but it's in the argument of this base 10 log. So the first thing to do, divide both sides by 10. So you get capital L divided by 10 equals the base 10 logarithm. You don't need to write base 10, but I'll write it anyway. The base 10 log of capital I divided by I sub 0. And then we can convert this logarithmic equation into an exponential equation using the base 10. The base 10 raised to the exponent capital L divided by 10 is equal to I divided by I sub 0. So the argument I divided by I sub 0 is equal to the base number 10 raised to the exponent L divided by 10. And now we're just one step away from solving for capital I. Just multiply both sides by I sub 0. And capital I is equal to I sub 0 times 10 raised to the exponent L divided by 10. And that's all you need to do on that one. The next equation, solve the equation capital M equals 8.8 plus 5.1 times the base 10 logarithm of capital D. Solve this for the variable D. So this comes from the field of astronomy. So to solve for capital D, we see that it's in the argument of this base 10 log. So first we isolate the base 10 log. We have to subtract 8.8 from both sides first. So M minus 8.8 equals 5.1 times the base 10 logarithm of capital D. Then divide both sides by 5.1. And we get M minus 8.8 all divided by 5.1 equals the base 10 logarithm of capital D. And now we can write the exponential equation that is equivalent to this logarithmic equation. The base of the logarithm is 10. So the base number 10 raised to the exponent, m minus 8.8 over 5.1, that will be equal to the argument of the logarithm, which is d. So I'll just write it as d equals the base 10 exponential with the exponent m minus 8.8 all divided by 5.1. And that's all we have to do on that one. Okay, the next equation, solve this equation, negative 1 over k times the natural log of capital P over 14.7 equals capital A. Solve this for capital P. The variable that we want to solve for is inside the argument of this natural logarithm. This is the base e logarithm. So first we want to isolate the natural log of P over 14.7. So if we multiply both sides by negative k times negative 1 over k is positive 1. So multiply both sides by negative k, we get the natural log of capital P over 14.7 equals negative k times capital A. Okay, this is the base e logarithm, so we can convert this logarithmic equation to its exponential equation equivalent. That means the argument of the logarithm, capital P divided by 14.7, is equal to the base number e raised to the exponent, negative k times a. And then the last step, multiply both sides by 14.7. And so capital P is equal to 14.7 times e to the negative k times capital A. Okay, now we'll start talking about continuous exponential growth and continuous exponential decay models. So there are some things nice about the continuous exponential growth and exponential decay models. As you will see shortly. But first, this paragraph, since many exponential growth and decay models are functions of time, the domain variable t is used instead of x. Any variables may be used, but some variables are more suggestive than others. So for both the exponential growth and exponential decay models, we may use this model, y equals y sub 0 times e to the k times t. Regardless of whether it's exponential growth or exponential decay, y sub 0 represents the initial value of the quantity y when t equals 0. So you can verify that if you replace t with 0. E to the k times 0 is e to the 0, but e to the 0 is 1, so the y value is y sub 0 when t equals 0. Y sub 0 is just the initial value. For continuous exponential growth, when we use this model, y equals y sub 0 times e to the exponent k times t, if the k value is positive, meaning that it's greater than 0, then you automatically know just by looking that you have exponential growth. So you'll see some terms used. When k is greater than 0, k is called the continuous exponential growth constant. Sometimes it's just called the growth constant. Sometimes it's called the growth parameter. But at the very least, if it's growth, it has to be positive. So another description might be if in this setting of continuous exponential growth, a growth rate parameter is given as a percentage, then K is just the decimal form of that percentage. If you look closely in the Alex homework, you'll probably see those exact words, growth rate parameter given as a percentage. So the K value is just the decimal form of that percentage. Okay, for continuous exponential decay, well, the model looks exactly the same, y equals y sub 0 times e to the kt, but if it's exponential decay, the number k is negative. So you can always tell just by looking whether it's exponential growth or exponential decay. Okay, so when k is less than 0, k is called the continuous exponential decay constant, or just the decay constant or decay parameter. And similar to what was noted above, if in this setting of continuous exponential decay, a decay rate parameter is given as a percentage, then the k is the negative of the decimal form of that percentage. Just always remember that if it's exponential decay, then this number k has to be negative. Okay, there's nothing magical about the variables that we were using up here. Other variables may be used. Just make sure that you're consistent and don't break any rules. Always follow the properties of exponents and logarithms. Okay, but we already know one continuous exponential growth model that we've had examples of already. So, for example, suppose a principal of capital P dollars is invested into an account with the annual interest rate R in decimal form. If interest is compounded continuously, then the amount of dollars, capital A, in the investment account after T years is capital A equals capital P times e to the RT. Different letters are used, but this has the same form as what we were just talking about earlier. So instead of y, we're using capital A. Instead of y sub 0, we're using capital P. And instead of k, we're using lowercase r. Okay, now we'll look at some examples. These are run-of-the-mill type of examples. They can be more complicated than this, but if you understand the simpler ones, then working with the more challenging ones will be that much easier. So in this one, the population of a town was 180 in January of 1980. And then in January 1986, the population was 200. So we'll assume exponential growth and then find a continuous exponential growth model. In all actuality, it might not be the case that the population is growing exponentially. But if it is, we can find a model for the exponential growth. So let's just start by writing y equals y sub 0 times e to the kt. And t is going to be the number of years since January of 1980. So t equals 0 corresponds to January 1980. The initial population, y sub 0, is given to be 180. So I'll write y sub 0 is equal to 180. And then we're told that 6 years later, in January of 1986, the population was 200. So we can write this down as, just to be more descriptive, when t is 6 years, I'll just say when t equals 6, the population y is 200. Okay, so we can use this information to determine what the growth constant k is, continuous growth constant k. Just one other thing first. When defining or finding an exponential growth model, there are two numbers that we want to find. That's the initial quantity, y sub 0, and the other one is the continuous exponential growth constant, k. We're already told what y sub 0 is. Now with the other information, we can determine what the value of k is, and then we will be able to write the complete model for this particular population. Okay, so when t equals 6, the y value or the population is 200. We already know that y sub 0 is 180, so we write 180 times e to the 6k. We replace t with 6. And then we just solve this equation for k. We know how to solve equations like this. K is in the exponent. So step 1, divide both sides by 180. And 200 divided by 180 simplifies to 10 over 9. So I'll just write it as 10 over 9. That's equal to e to the 6k. And then we'll take the natural log of both sides. So the natural log of 10/9 equals the natural log of e to the 6k. And hopefully you'll remember the natural log is the base e. So the natural log of e to the 6k is just 6k, because the base number e raised to the 6k is equal to the base number e raised to the 6k. Just applying the definition of a logarithm. So the growth constant, continuous growth constant k is the natural log of 10/9 divided by 6. Okay, I sort of ran out of space to write the continuous exponential growth model. So I'll write it in part B because we're going to use it in part B. So it's y equals the initial population of 180 times e to the kt, but this time instead of writing the letter k, we'll write what the actual value of k is, the natural log of 10/9 over 6t. Okay, so this says find the size of the population in January 2010. Okay, so the value of t is 30. So if you remember, t equals 0 corresponds to January 1980. And in January of 2010, that's 30 years later, so t is 30. Okay, so all we have to do, if you just want an answer that's not an actual integer, where you would round to the nearest integer, just replace t with 30, so we get 180 times e to the natural log of 10/9 over 6 times 30. So on next Friday's test, this is a satisfactory answer. But do practice with a calculator how to convert this to an actual number that you can relate to. And populations are typically rounded to the nearest whole number. Okay, then in part C, find the doubling time. That's the amount of time it takes for the quantity to double. So we'll write down the model, as tedious as that may be. y equals 180 times e to the natural log of 10/9 over 6 times t. So the doubling time, we want to find the amount of time t, find the value of t when y is 2 times the initial population. So when y is 360. Okay, so what we're going to do, and we know how to do this, just replace y with 360 and proceed to solve that equation for t. Okay, replace y with 60 or 360. 360 equals 180 times e to the natural log of 10/9 over 6 times t. Then divide both sides by 180. 360 divided by 180 is just 2, so we get 2 equals e to the exponent natural log of 10/9 over 6t. We want to solve for t, but t is in the exponent, so we take the natural log of both sides. Okay, so the natural log of 2 on the left-hand side. And if you'll allow me a little leeway, when we take the natural log of e raised to an exponent, it's just going to simplify to the exponent. We saw that earlier. So the natural log of e to this exponent simplifies to the exponent. So the exponent is the natural log of 10/9 over 6 times t. So now we can just multiply both sides of this equation by the reciprocal of the coefficient of t. So that is multiply both sides by 6 divided by the natural log of 10/9. And the doubling time will be 6 times the natural log of 2 divided by the natural log of 10/9. And this is measured in years. Okay, so for next Friday's test on a problem like this is an okay way to answer the number. Okay, let's look at another example. Example 2. So this one says, suppose 512 pounds of nuclear alloy shrinks to 64 pounds in exactly 12 days. So let's assume exponential decay. Find a continuous exponential decay model. Okay, so we start out by writing y equals y sub 0 times e to the kt. But we're expecting k to be negative since it's exponential decay. The initial quantity is given, y sub 0 equals 512. So in other words, when t equals 0 days, the quantity is 512. And then we're told that when t equals 12 days, the y value or the quantity will have shrunk to 64 pounds. So in other words, when t equals 12, the amount left will be just 64 pounds. So we'll use this information to solve for the decay constant. So replace y with 64. The initial quantity is 512. And we set that that's equal, 64 is equal to 512 times e to the 12t. I'm sorry. T the t value is 12, so it's 12k. Sorry. 64 equals 512 times e to the 12k. Okay, so we'll divide both sides by 512. Let's see. 512 is 2 to the 9th. 64 is 2 to the 6th. So 2 to the 6th divided by 2 to the 9th is 1 over 2 to the 3rd. So when I divide both sides by 512, I'm just going to get 1/8 equals e to the 12k. So writing 1/8 is easier than writing 64 over 512 numerous times. Okay, now we just take the natural log of both sides. We want to solve for k because it's in the exponent. So the natural log of 1/8 equals the natural log of e to the 12k, but the natural log of e to the 12k is just 12k. And if you want, you can convert 1/8 to 0.125 if you want. Either way is okay. But anyway, the decay constant is the natural log of 1/8 divided by 12. So some of you might be wondering, isn't k supposed to be a negative number? Well, this is a negative number. If you compute a logarithm of a number, that is, if the argument is a number between 0 and 1, then the logarithm of that number is negative. So the natural log of 1/8 is a negative number. So I think I'm going to go ahead and write it as the natural log of 0.125 instead of 1/8 over 12. And so our model for this one is y equals the initial quantity of 512 times e to the kt, but k is the natural log of 0.125. If you can read my writing, over 12 times t. Okay, then in part B, find the amount of nuclear allo left after exactly 8 days. So all we have to do is replace t with 8. And our exact answer in raw form is y equals 512 times e to the natural log of 0.125 over 12 times 8. Okay, find the half-life. The half-life is the amount of time it takes for the quantity to reduce by 1/2. So the initial amount is 512 pounds. And since we have exponential decay, then it's only a matter of time until the quantity left is 1/2 of the original amount. So I should write down the model again since it's out of sight. So y equals 512 times e to the natural log of 0.125 over 12 times t. So we want to find the half-life. That means find the value of t measured in days when y is equal to 256 pounds, which is 1/2 the initial quantity. Okay, so replace y with 256. Set that equal to 512 times e to the natural log of 0.125 over 12 times t. Divide both sides by 512. 256 divided by 512 is 1/2. So 1/2 equals e to the natural log of 0.125 over 12 times t. We want to solve for t, but t is in the exponent, so we take the natural log of both sides, the natural log of 1/2. And we're taking the natural log of e raised to the exponent, so it just simplifies to the exponent, the natural log of 0.125 over 12 times t. And we can get the half-life if we just multiply both sides of this equation by the reciprocal of the natural log of 0.125 over 12. So the half-life is 12 times the natural log of 1/2 divided by the natural log of 0.125. And this is measured in days. And just for practice, notice that this is a positive number. 12 is obviously positive. The natural log of 1/2 is negative, and the natural log of 0.125 is negative, so it is a positive number. Okay, a few more little exercises. We've already had practice doing some of this. So suppose capital P of t equals capital P sub 0 times e to the kt, where k is greater than 0 and t is a unit of time. So if k is greater than 0, it's continuous exponential growth. So there is a doubling time. So find a formula for doubling time. Okay, so in other words, find t when P of t is equal to 2 times the initial amount, when it's equal to 2 times P sub 0. So in the function, replace P of t with 2 times P sub 0, set that equal to P sub 0 times e to the kt, and then we're going to solve for t. That will be the doubling time. So first divide both sides by P sub 0, and we get 2 equals e to the kt. We want to solve for t. T is part of the exponent, so we take the natural log of 2, or natural log of both sides. So the natural log of 2 equals the natural log of e to the kt, but that simplifies to kt. And so the doubling time is the natural log of 2 divided by the continuous growth constant k. So the doubling time formula is the natural log of 2 divided by the continuous growth constant k. So this is a useful formula to remember. And it's also useful in part B. If you solve this equation for k, if you just first multiply both sides by k and then divide both sides by the doubling time, the continuous growth constant k is equal to the natural log of 2 divided by the doubling time. Okay, the next example is very similar. Since we're getting a little short on time, you can probably guess what the formula for half-life is. It's going to follow a similar type of, exponential growth is different from exponential decay, but there are certain things that are similar. So the half-life is just going to be the natural log of 1/2 divided by the decay, the continuous decay constant. And then in part B, if you solve this equation for the decay constant, it's equal to the natural log of 1/2 divided by the half-life. So even though I didn't go through the steps, if you want to on your own, you can follow what we did in number 1, parts A and B, and just apply them to this function using half-life instead of doubling time. You'll get the same results. Okay, one last thing, and then we'll be able to start the quiz. Use a high-powered calculator, the natural log of 2. Knowing what the natural log of 2 is in decimal form is sort of handy. The natural log of 2 is just 0.6931471806, and then it's a non-terminating decimal, but if you can write it out to 10 decimal places, that's a pretty good approximation. The natural log of 1/2, well, I'll just tell you what it is, but if you know what the natural log of 2 is, you can use properties of exponents and logarithms to determine what the natural log of 1/2 is. This is just the negative of 0.6931471806, and so on. Okay, so I think we'll stop there, and I'll go to my office and email the quiz.